In lesson 2, our goal is to evaluate limits analytically. And for this lesson, we're going to focus on where our function is continuous, where we have a jump or a hole. In the next lesson, we will talk about vertical asymptotes and how to evaluate limits and end behavior. So when we're evaluating limits analytically, what we mean by that is from the equation. So we don't have the picture, we don't have the graph. Okay, so first thing that we would want to consider is that we know from the definition of continuity that if a function is continuous, its limit value is equal to the function value at that particular value x equals a. So for our first example, we already know that this function is continuous at x equals 2, but let's pretend that we didn't. If I just look at x plus 3 divided by x minus 1, I know the only discontinuity is going to happen when x equals 1, because that's the value that will make my denominator equal to 0. And since this isn't a piecewise function, I'm not worried about jumps. So while this function does have an asymptote at x equals 1, we're evaluating the limit of the function as x approaches 2. So because our function is continuous, this is the same as just plugging in 2 for x and getting the function value. Generally speaking, anytime we evaluate a limit, we always want to start by plugging in our function value. So our limit as x approaches 2 of x plus 3 over x minus 1 is just 2 plus 3 over 2 minus 1, which is 5 over 1. Let's try the second example. So again, I could look at the denominator of this function, and I know the only place where I'm going to have some type of discontinuity is where my denominator is equal to 0, because my sine function is continuous everywhere. So I know, for example, when x is equal to pi, that I will have a discontinuity. But since x is approaching pi over 2, we're evaluating the limit as x approaches pi over 2 of sine of x over x minus pi. I know that I don't need to worry about a discontinuity. So again, I'm just going to plug it in. I'm going to encourage you to practice the limit notation. AP is very picky about it when we grade free response questions, so you'll see me always practice it. All right, so we need the sine of pi over 2 divided by pi over 2 minus pi. All right, so the sine of pi over 2, if you recall your unit circle, we know that pi over 2 radians is at the top of our unit circle. And if I think of my unit circle, I'll try to draw a circle. Could be better. If I remember my unit circle, the ordered pair at the top is 0, 1, and my unit circle is cosine, sine. So cosine theta, sine theta, if we want to call that angle theta. So I know that the sine of pi over 2 is equal to 1. And I need to do something about my denominator. Something we could do, there's a couple ways, like we could just get common denominators to evaluate this. Or if I want to get rid of that fraction, if I want to get rid of this little 2 in my fraction, in my opinion, the easiest thing to do is to multiply the entire bottom of this by 2. And if whatever I do to the bottom, I know I need to do to the top of my fraction, well, as far as multiplication and division go, so I can multiply the top by 2 as well. And when I do that, I end up getting a 2 on top. And on the bottom, I'm going to distribute this 2 to both terms. So I end up getting pi minus 2 pi. And now I could just do that subtraction, right? 1 pi minus 2 pi is negative pi. Or I could think of this as just negative 2 over pi. So there's a lot of ways to get to that final answer. You might have done it differently, but we need to make sure that we can simplify that. All right, so in summary, when our function is continuous, we can evaluate the limit, and we'll know our function's continuous because when we plug in, for example, pi over 2 in that last example, we get a value. So when we evaluate our limit, and by plugging in, we just get a number, we don't get something over 0 or 0 over 0, then we're in good shape. We know our function's continuous there. So now on to jumps. We know, again, that a jump can only occur at the boundary of a piecewise function. So again, by the boundary in this first example, I mean x equals 1. So it's at 1 that we jump from being a, well, I shouldn't use the word jump in that way, but it's at 1 that we switch from being a linear equation, x plus 5, to a quadratic function, x squared plus 2. So anytime we evaluate the limit at a boundary of a piecewise, we have to check both sides, because if we don't, it's possible that the limit does not exist. So remember, the limits from the left and right must agree. Now, it's not always easy to sketch a graph of a piecewise function. I think for this function, it's easy because this function is linear and quadratic. Oh no, I don't know what happened to my, oh, I know what I just did. Sorry, I was trying to draw a picture and I was using the wrong tool. Okay, so I know that this function is going to be, so like if I start from the left, a line of x plus 5. So let's say that this is 5 on my y-axis. So this would be up here at 6. I'm going to make that an open circle because our function, when x equals 1, we're going to use the bottom piece, not the top piece. But x plus 5 might look like that. And then on bottom, we have this quadratic x squared plus 2. So if I plug in a 1 to that, 1 squared plus 2 is 3. So I'm just going to say that 3 would be about there. And I know that that's actually the vertex of my parabola because x squared plus 2 is just, no, I'm sorry, that's not the vertex of my parabola, excuse me. The vertex would be right here. Oh, wow, I'm not gonna fix that in the video. I'm just gonna keep on moving. Our vertex would be when x is 0 because that is just like a k transformation. We're just shifted up 2. So this is the parent function x squared shifted up 2 units. Okay, so our graph looks something like this. Now again, our whole purpose of doing this is to do this analytically, so we don't need to know what the graph looks like, but it is helpful when we can visualize what we're doing. All right, so the first thing is we're asked to evaluate the limit of f as x approaches 1 from the left. And again, it's that little negative symbol that tells us we're coming from the left. Because we were able to draw this graph, we kind of know visually what we're expecting to see there. But if I'm evaluating this limit, I just want to make sure to use the correct piece from my piecewise function. So again, if I'm approaching the number 1 from the left of the graph, I'm approaching 1 from numbers that are less than 1. So I know I want to use this top piece. So this limit is going to just be equal to the limit as x approaches 1 from the left of x plus 5. And so that's just going to be 1 plus 5, which is 6. And again, we could see that visually on the graph we sketched that we would expect from the left this line to be approaching the number 6. All right, then our next question is to evaluate the limit of f as x approaches 1. So not from one side or the other, but just what is the limit? So to do this, we need to know the limit of f as x approaches 1 from the right. So as we approach 1 from the right, we're going to use the bottom piece, the x squared plus 2. So that's going to become 1 squared plus 2, which is just 3. And we also know that that is equal to f of 3 because we have that greater than or equal to symbol on our boundary of our piecewise. So the final question, well, we're asked to evaluate this limit and determine if f is continuous at x equals 1. Well, what we need to say is that the limit of f as x approaches 1 does not exist or is non-existent. And again, the reason that it's non-existent is because our limit of f as x approaches 1 from the left is not equal to our limit as we approach 1 from the right of f of x. So if those two one-sided limits don't agree, then the limit does not exist. And if those limits don't agree, or if the limit does not exist, our function is not continuous at x equals 1 either. So for that same reasoning, f is not continuous at x equals 1. All right, let's look at our next example of the piecewise. We're given, or example of jumps, I should say. We're given a piecewise G, and you might notice something interesting about the boundaries. Instead of having inequalities like x is less than 3 or greater than 3, we instead have an equal to and it does not equal to. So x equals 3 and x does not equal 3. Now, if you wanted to, you could actually rewrite this as inequalities. We don't need to, but I could think of G that for values of x that are less than 3, that I've got the tangent of pi over 4x. Then for values of x that are equal to 3, my function value is -1. And then for values of x, oops, I don't know why I wrote a 3 there. For values of x that are greater than 3, I would go back to tan of pi fourths x. So we can split this does not equal to into two different inequalities. I don't know why I keep writing the number 3 when I mean to write the number 4 and vice versa. Double check me there. All right, so we could actually break this into two different inequalities. We don't need to, but we can. So basically, our function g is almost always the tangent of pi over 4 times x, except for the one particular input of 3. And when x equals 3, g is just -1. So when we're evaluating this limit as x approaches 3 of g, we said that we need to make sure the left and the right-sided limits agree. Well, when we write it this way, this is to the left of 3. This is the piece we use to the right of 3. So more generally, going back to our original piecewise, if I'm approaching 3 from the left and the right, and I'm just not at 3, that's going to be every value of x on the number line that does not equal 3. So when we evaluate from our original piecewise this limit, this is the left and the right-sided limit, because if we're approaching 3 from values of x not equal to 3, that's going to be numbers that are both, or not both, but either less than 3 or greater than 3. Okay, so our limit of g as x approaches 3 is the tangent of 3 pi over 4. And again, we're not using the -1 here because this is g of 3. And remember, a limit is how our function behaves as we approach a value. It's where our function is headed. It's not necessarily the function value. Now, I need to go back to my unit circle, and this is a good time to, like, if you haven't reviewed the unit circle since last year or the year before, it would be smart to kind of go back and study that. When I'm working with something with a denominator of 4, I like to think that if I start at 0 radians, then I have pi over 4. Then I have 2 pi over 4, which is just pi over 2. Then I have 3 pi over 4. And if I continue, I would have 4 pi over 4, which is just pi. So I need to know the tangent of 3 pi over 4. Now, if I evaluate the tangent of something that's divisible by 4, I'm going to have a 1 or a -1, right? If I think about it, I'm going back to my isosceles right triangle. So sine and cosine are going to have the same value. They just might not have the same sign. So I could actually divide my sine by cosine. If I remember this ordered pair from the unit circle, it's going to be -√2 over 2, comma √2 over 2. I could think of it that way and literally divide. Or I could just remember that the tangent of 3 pi over 4 is going to be -1 because we're in the second quadrant where cosine is negative, sine is positive, x is negative, y is positive, and this is an isosceles right triangle. So sine and cosine, their absolute value is the same. Okay, so we should get a -1 there. Okay, so our second question, is G continuous at x equals 3? And going back to the definition of continuity, for G to be continuous at x equals 3, it must be the case that the limit of G as x approaches 3, first of all, it has to exist. And we know it does, we just found it, it's -1. But that must also equal G of 3, which from the piecewise we can tell it does, because we know from our piecewise that G of 3 is equal to -1. So because those statements are true, we could say that yes, G is continuous at x equals 3. All right, the final example that we're going to do for jumps involves absolute value. So when we talk about the absolute value, like anytime we have a function with absolute value in it, it's important to remember that the absolute value function is a piecewise defined function. So for example, if I were to just graph y equals the absolute value of x, well, I know that on the right-hand side, so like starting at my vertex 0, 0, that this is just a line with a slope of 1. But I know on my left-hand side that all of my negative x inputs become positive y outputs. So I have a line with the slope of -1. So if we were to write y equals the absolute value of x as a piecewise defined function, for values of x that are greater than or equal to 0, it's just x. For values of x less than 0, we just multiply them by -1 to get a positive number, so -x. So in this example, when we have this rational function that has a piecewise numerator, I personally would start with just the numerator. So if I were to write, let's say, the absolute value of x minus 2, if I'm trying to define this as a piecewise function, well, this is going to be the function x minus 2 anytime x minus 2 is greater than or equal to 0. So basically, if the expression x minus 2 is positive, then I'm just going to use x minus 2. However, if my expression x minus 2 yields a negative number, I know to find the absolute value, I would have to take the opposite. So multiply this by -1. So again, I'm going to do this anytime x minus 2 yields a negative number, a negative value. So we could start writing our piecewise this way. However, what I would do is I would clean up the boundaries. I don't want my boundary to be where x minus 2 is greater than or equal to 0. I want to really add that 2 over and say that this boundary is when x is greater than or equal to 2. And down here in this bottom inequality, I want to add 2 to both sides and say this boundary is for values of x that are less than 2. But we could always start with what's in our piecewise function. So now let's take this one step further. We said this is not the function we're working with. This is just the numerator. But if I wanted to rewrite my expression x minus 2, the absolute value of x minus 2 divided by x minus 2, if I want to write this as a piecewise function, we could use what we have above to help us. So I know that when values of x minus 2 are positive, meaning x is greater than or equal to 2, this is just going to be my numerator. So x minus 2 over x minus 2. And again, we said that's for values of x that are greater than or equal to 2. So I'm using this kind of simplified version of our boundary. And then for values of x that are less than 2, I'm going to use this as my numerator. I'm not going to distribute that negative. I'm just going to keep it out front. My denominator is x minus 2. And again, that's for values of x that are less than 2. Okay, so now we have rewritten this expression as a piecewise defined function, but I actually think there's one more way that we could simple this up. I might notice that x minus 2 divided by x minus 2, that's always going to be the number 1. Like that's going to be 1 for any value of x that I plug in. So pop this up here. As I rewrite this one final time, hopefully, I know that my function is actually going to be positive 1 for values of x that are greater than or equal to 2. And if I come back to the second piece, well, that's just negative 1. It's x minus 2 divided by x minus 2 times a negative. So I know that my function is actually just negative 1 for values of x that are less than 2. So again, we don't have to, oh, I just caught myself doing something. We don't have to draw this picture, but it might be helpful to draw the picture. I'm realizing though that I made a mistake back here in the blue spot, that as soon as we went back to divide by x minus 2, I should actually just drop that or equal to sign, leave that as x is greater than 2. I'm going to do the same over here in this other piecewise. And the reason for that is that if we actually plug 2 in, we're going to have a discontinuity. We're going to have a hole in the graph, so we cannot evaluate this piecewise for x equals 2. So when we go to sketch this, the reason that's, I don't know, it's important to think about, I suppose, is that if I were to sketch this, we said for values of x less than 2, so like 1, 2, we said that this is going to be just negative 1. So I should have an open circle there, and it's a horizontal line. And then for values of x greater than 2, so it's 1, it's negative 1, I'm just going to have positive 1. But both of those should be open circles, not closed circles when we sketch that. Okay, so going back to what we were actually trying to do to evaluate this limit. Once we have written this as a piecewise defined function, and again, we'll see this on the graph, but we're trying to do this analytically. When we evaluate this limit, we need to evaluate the limit from the left and right separately. So my limit as x approaches 2 from the left of our function, well, if I look, there's nothing to plug in here. Oh, sorry, that was from the right-hand side. There's nothing to plug in here. That's just negative 1. That's all I'm going to write. As we approach from the other direction, so the limit as x approaches 2 from the right, well, that's just positive 1. Okay, so we could see that from our graph. As I approach 2 from the left, I'm approaching, my y value is approaching negative 1. As I approach 2 from the right, my output's approaching positive 1, or we can do that analytically. So all that to say, the limit does not exist because those two numbers don't agree. So the limit as x approaches 2 is non-existent. And again, the reason for that is because the limit of the absolute value of x minus 2 divided by x minus 2 as we approach 2 from the left is not equal to the limit as we approach 2 from the right.